Hello learners, welcome to online video lectures on subject heat and mass transfer. In present session, we are going to discuss problems on free and forced convection part 2nd. Those who have not viewed my previous video on the problems on free and forced convection part 1 must see, so that I have given the introductory part of the dimensionless number and how these dimensionless numbers are useful to solve the problems on free and forced convection. So let's solve the next problem. A flat plate of 1 meter width and 1.5 meter length. So I have drawn a simple diagram of 1.5 meter length and 1 meter width is to be maintained at 90 degrees centigrade. So surface temperature of the plate is 90 degree centigrade. In air with a free stream temperature is 10 degrees centigrade. So I have told you that for free stream temperature we consider T infinity, which is a 10 degrees centigrade. Determine the velocity with which air must flow. We have to determine U over the plate along 1.5 meter side. You keep in mind while solving the problem, it is very important to know from which direction air is flowing, either from length or from width side, otherwise your solution may get completely wrong. So we have to determine the velocity with which from 1.5 meter side, so that the rate of heat or energy dissipation from the plate is 3.75 kilowatt. First time in the problem, Q value is directly given and we have to calculate the U. Take the following properties of the air at 50. If you don't know how to take the properties of air at 50, I told you that you have to do the addition of plate temperature 90 plus free stream temperature 10. 90 plus 10 is 100 divided by 2, so it will become 50. And from the data book we have to get the data for the air at 50 degrees centigrade. It is directly given in the problem, so no worries. Rho means density, K is thermal conductivity, C is specific heat, mu is the viscosity, and Prandtl number 0.7. And in each problem the relation for H, that is convective heat transfer coefficient, is given. And once again I repeat for you, if there is a need to calculate the value of U, or if the value of U is given, definitely problem belongs to forced convection, or in this relation Reynolds number is given, it means the problem directly belongs to forced convection. Then from this data I have taken this value from the problem. Then let's solve the problem. We have to calculate the free stream velocity. We know that according to the Newton's law of cooling, Q is equal to HA delta T. So from this we can calculate the value of U. So before begins we can calculate the H, that is convective heat transfer coefficient, and for this the relation is given K divided by L, Reynolds number and Prandtl number. The K directly taken from the table, L length that is 1.5, Prandtl number is given 0.7, and we know the formula for Reynolds number, that is in case when the mu is given formula is different, when nu is given formula is different. So here mu, that is viscosity, is given, so we have to use the formula rho Lu upon mu, or if it is nu is given, that is kinematic viscosity, the formula will be Lu upon nu. So keep in mind for this condition, and from this we can calculate the value of H, but here U is unknown, so that we have to calculate. So the value of H becomes 3.123 into root U. This is the unknown value, we cannot determine the exact value of H. But in this problem Q is given, then A area is given 1.5 into 1, surface temperature is given, infinity temperature, that is free stream temperature, is given. By this relation you can calculate the value of U as 100 meter per second. This is the first problem where we have calculated the free stream velocity. Then we will go to the next problem. A hot plate of 1 meter and 0.5 meter is at 130 degrees centigrade kept vertically in a still air at 20 degrees centigrade. So dimensions of the plate are given. Then 130 degrees is the surface temperature of the plate. Okay, here Tp is given, or we can write Ts, and atmospheric temperature Ta is given, so you can take infinity also, T infinity as 20 degrees centigrade, and we have to calculate heat transfer coefficient H and initial rate of cooling. In this problem their initial velocity of air is not given, means u is not important. So in this case the problem belongs to free convection, keep in mind. Otherwise you see here, assume 0.5 meter side is vertical and that heat transfer coefficient is calculated, above remains constant and convection takes place from both sides of the plate. So in this problem also you keep in mind heat transfer taking place from both the side. Or in this equation you can see Nusselt number is calculated by GR and PR. PR means Prandtl number, GR means Grashoff's number. You keep in mind whenever there is a Grashoff's number, the problem directly belongs to free convection. Then properties of the air are taken similar fashion. 130 degrees the temperature of plate plus 20 degrees the free stream temperature divided by 2, 75 degrees centigrade. If this data is not given in the examination, you have to use the table, and the properties of air at 75 degrees centigrade we have to list it down, and this data is directly given in the problem. So let's solve the problem. So first of all we have to calculate Prandtl number. If you have the value of Prandtl number directly given, then it is okay. If it is not given, we have to calculate by mu Cp upon K. By this we can get the value of Prandtl number. Then we have to know the formula of Grashoff's number. L cube G beta into bracket Ts minus T infinity divided by nu square. Nu is a kinematic viscosity, and putting this value you will get the value of Grashoff's number. Then we have to take the product of Grashoff's number into Prandtl number and put this product into the Nusselt number, so we will get the value of Nusselt number. And finally you know that Nusselt number is equal to HL upon K, and we know that from this formula you can calculate the value of H, that is 5.66 watts per meter degree centigrade. Further we have to calculate the initial rate of cooling. As I told you that initial rate of cooling means delta T, and in this problem heat transfer is taking place from both the sides, so Q is equal to 2 into HA delta T. Just now we have calculated the value of H. A is the surface area of the plate, temperature difference is there, and Q is directly given in the problem. So from this equation we can calculate the delta T, that is delta T is nothing but 4.668 degree centigrade per minute. It is a rate of cooling, so we have to calculate in terms of degree centigrade per minute. And the last problem we are going to discuss is a square plate of 40 centimeter to 40 centimeter. You see in every problem the dimensions are given in a different fashion. Sometimes it is given in the meter, sometimes given in the millimeter, sometimes it is given in the centimeter, but in SI unit we have to convert this into meters. Is maintained at 400 degree Kelvin or Kelvin. The temperature may either given in the degree centigrade or in the Kelvin. Is suspended vertically, means a square plate of temperature 400 Kelvin is suspended vertically like in the previous problem at an atmospheric temperature of 300, means this is a free stream temperature. Now we have to determine the boundary layer thickness at trailing edge of the plate, and number 2 we have to calculate average heat transfer coefficient by using this relation. Again in this problem Grashoff's number is given, mean this problem belongs to the free convection. Again I repeat to you, if these properties of air are not given, we have to make the addition 400 plus 300 700 divided by 2, and accordingly we have to go for log data table, and from data table we have to obtain these values. And one more condition is given. This is the first time problem we are discussing. The boundary layer thickness is given by boundary layer thickness x. X is the thickness of the plate, that is 40 centimeter or 40 millimeter, sorry 400 millimeter or 0.4 meter. And here Prandtl number, Grashoff's number, Prandtl number. So to calculate this delta we have to calculate the Prandtl number as well as Grashoff's number, and by using these two number we can calculate Nusselt number, and by using Nusselt number we can calculate the other required things. So let's solve the problem. So to calculate the boundary layer thickness we have the relationship this, so Prandtl number and Grashoff's number. We know the formula of Grashoff's number, x cube. Sometimes we use the L as the thickness, so you can take either L or X, no problem. So x cube G beta delta T divided by nu square, kinematic viscosity. So put all these values, already we have taken in the given data over here. By this we can take the Grashoff's number. Second condition is a Prandtl number. Prandtl number is already given in the problem, that is 0.7. So directly we know the Grashopp's number, we know the Prandtl number, put the value in the thickness, so you will get the thickness, that is 0.0149 meters, or you can convert into millimeter, but mostly put your answer in the meter as a SI unit. Second question is average heat transfer coefficient H. We know that if you have the Grashopp's and Prandtl number, we can calculate the Nusselt number. This relation is already given in the problem. See here, the relation is already given. Then we know that Nusselt number is equal to HL upon K, and we have already calculated Grashopp's number. We have already know the Prandtl number. Then by putting this, we can calculate convective heat transfer coefficient as 5.058 watts per meter square degree centigrade. So in this chapter we have to practice more on the problem for better understanding. Thank you.